extrinsic semiconductors. Since semiconductors are generally poor conductors, their conductivity can be drastically increased by the controlled addition of impurities to the intrinsic or pure semiconductive material. It means extrinsic semiconductors have impurities. Doping is a phenomena in which addition of external impurities to the host atom takes place. These host atoms can be silicon or germanium. This doping alters the electrical or resistive properties of the material. It increases the number of current carriers, that is, electrons or holes. These doped semiconductors are those in which one kind of carrier predominates in a controlled way. An extrinsic semiconductor can be further classified into two types. First is N-type semiconductor and second is P-type semiconductor. Now we will talk about N-type semiconductor. In N-type semiconductor, pentavalent impurity atoms are added to increase the number of conduction band electrons in intrinsic host atom. These pentavalent impurity atoms are atoms with 5 valence electrons such as arsenic, phosphorus, antimony, etc. These atoms introduce free electrons in the host atom. The number of free electrons depends on the amount of impurity added to the intrinsic host atom. A small addition of impurity generates millions of free electrons. Therefore, such impurity is also known as donor impurity. Since the pentavalent atom gives up an electron, it is often called a donor atom. This type of doping is also called pentavalent doping. In N-type semiconductors, electrons are the majority carriers and holes are the minority carriers. It is measured in electrons per cubic centimeter. Now, look at this figure. We know that there are 5 valence electrons in the phosphorus atom and 4 valence electrons in the silicon atom. So, when this phosphorus atom is added to pure silicon, then 4 out of 5 valence electrons of this phosphorus atom make covalent bonds with neighboring silicon atoms, as you can see here. As a result, the 5th valence electron of this phosphorus atom becomes free. It becomes a conduction electron. The number of conduction electrons can be carefully controlled by the number of impurity atoms added to the pure silicon. Now we will talk about P-type semiconductor. In P-type semiconductor, trivalent impurity atoms are added to increase the number of holes in intrinsic host atom. These trivalent impurity atoms are atoms with 3 valence electrons such as boron, indium and gallium. These atoms introduce shortage of electrons, that is, holes, in the host atom. The number of holes can be carefully controlled by the number of trivalent impurity atoms added to the host atom. Such impurity is known as acceptor impurity. Since the trivalent atom can take an electron, it is also known as an acceptor atom. This type of doping is also called trivalent doping. In p-type semiconductors, electrons are the minority carriers and holes are the majority carriers. It is measured in holes per cubic centimeter. Now, look at this figure. We know that there are 3 valence electrons in boron atom and 4 valence electrons in silicon atom. So, when this boron atom is added to pure silicon, 3 valence electrons of this boron atom make covalent bonds with neighboring silicon atoms, as you can see here, and lack of one electron gives rise to a hole in this p-type semiconductor.